Good morning students. In the previous video lecture we have discussed about the instruction sets of 8085 microprocessor and also the interrupt structure of 8085 microprocessor. Now in this video lecture we will be discussing about the instruction execution and timing diagram of 8085 microprocessor. Before discussing about the timing diagram in detail, let us have a quick review on the basics of microprocessor what we have discussed earlier. Basically, microprocessor performs two tasks: instruction fetch and instruction execution operation. During the instruction fetch operation, the microprocessor fetches all the bytes of current instruction from memory. The first byte of instruction is always a opcode. Microprocessor executes a special fetch or read cycle to fetch the opcode called opcode fetch cycle. Next, the second basic operation what the microprocessor will do is instruction execution operation. The instruction execution operation has two categories: internal operation and external operation. Internal operation is nothing but of performing arithmetic, logical, decision making and internal data transfer operation by microprocessor or called as internal operation. External operation are nothing but of data reading, data writing, stack reading, stack writing from the memory, or IO read, input output read and input output write operation performed through input output devices. These operations are being called as external operation. Hence, as soon as the microprocessor wants to perform an operation, it first fetches or read the opcode from the memory. Right? After taking the data from memory or opcode from memory, it enters into the execution operation. The execution operation executes the particular opcode. Let us now discuss about the representation of signals in timing diagram. There are different types of signals represented in timing diagram. They are listed here: clock signal, single line signal, multiple line signal, multiple lines with high impedance, single line and single effect signal, multiple line and single effect signal. Let us discuss in detail about each and every signal now. Now let us discuss about the clock signal. Microprocessor operates with reference to the clock signal provided to it. We have already discussed about it while we are discussing about the pin diagram. I have told that pin number X1 and X2, pin named X1 and X2 are being connected with the external crystal oscillator, and the frequency generated by means of that crystal oscillator is made used by the microprocessor for its operation. Basically, clock signal is a square signal. Microprocessor is very fast. Whatever time taken from low state to high state, it matters for the microprocessor. So, in the second diagram, you can see that the increasing pulse or decreasing pulse has a certain time. So we can understand that a cycle is from transition from 1 to 0. Transition from 1 to 0 is called a cycle or 1 T state. Right? Suppose if the external connected crystal oscillator is of 6 megahertz, then half of the 6 megahertz is nothing but of the operating frequency. That is, the microprocessor will operate at 3 megahertz frequency. If the external clock frequency is 4 megahertz, then the operating frequency of microprocessor is 2 megahertz, right? So half of the crystal oscillator frequency is nothing but of the operating frequency of a microprocessor. Next we discuss about the single line signal. The status of single line will be either low or high, but the change from one state to another state is not possible. The status of single line will be either low or high, but the change from one state to another state is not possible in zero time, right? Next, we discuss about multiple line signals. In microprocessor, we have multiple lines. These signals are called as bus signals. If a single line change occurs, then we have to show a cross to indicate the change in the content. So such lines are called multiple line signals. Next, we discuss about multiple line with high impedance. Multiple lines with high impedance. This multiple line with high impedance, this is also of bus signals, right? The processor completes the execution of current machine cycle and floats the address, data and control lines, right? After the microprocessor completes the execution of current machine cycle, the processor will float the address, data and control line by means of the high impedance state or tri-state. So once the microprocessor is in tri-state, what it is going to do? It is going to float the address, data and control lines, right? So when it does, once the current execution is being completed, once the current machine cycle is being completed, it is going to float the address, data and control lines during this high impedance state or tri-state. That is being represented by this multiple line with high impedance. Next we will discuss about single line single effect signal. Single line single effect signal. I have shown an example for single line single effect signal here. As we see the line 1 is initially in high state and it goes to low state after a quiet while. While the line 1 is in high state, you see the line 2 is in low state. As soon as the line 1 goes to the low state, we can see that line 2 slowly changes from the low state to high state. That is, it means that a single effect in line 1 signal is going to make an effect on the line 2 signal. A single effect, that is a single effect on line 1 is going to make a change on the line 2 signal. That is, as initially it is in 1 state, when it goes to 0, what happens? The line 2, which is in 0 state, moves to state 1, right? Similarly, we can compare this signal line 1 to single line 3. So line 1, you can see that when a complete clock cycle is over, that is a transition from 1 to 0 is over, until that the line 3 is in state 1, isn't it? So once it complete a clock cycle or T state, the line 3 changes from 1 to 0 state. So a complete effect on line 1, that is after one clock state, line 3 is going to change from 1 to 0. This is being called as single line, single effect signal. Next is about multiple line single effect signal. I have shown an example over here. The line 1 is initially in 1 state, line 2 is in 0 state, and line 1 is in 1 state. Right? As soon as line 1 goes from 1 to 0, we can see that the line 2 goes from 0 to 1 state, and as soon as line 2 start moving from 0 to 1 state during the rising edge of the signal, what happens to line 3? The line 3 is moving from 1 to 0 state. Right? This is being called as multiple line and single effect signal. So multiple lines are there. A single effect on the signal is going to make changes, make effects on the multiple lines. Right? Let us get into timing diagram. What is a timing diagram? Timing diagram is a graphical representation. It represents the execution time taken by each instruction in a graphical format. The execution time is represented in T states. I will tell you what is a T state. Next, instruction cycle. Instruction cycle is the time required to execute an instruction. We all know that microprocessor will execute the instruction which are all being given by means of a user. So the time required to execute an instruction is called an instruction cycle. The time required to access the memory or input output device while the microprocessor is executing, before executing the instruction, what the microprocessor have to do? The microprocessor have to fetch the opcode or data from the memory, so that it will take some time to access the memory, right? So the time required to access the memory or input output device is called a machine cycle. The time required to access the memory or input output device is called machine cycle, and instruction cycle is nothing but of the time required to execute an instruction. Next, T state. The machine cycle and instruction cycle takes multiple clock periods. I have told that while we are defining the instruction cycle, I have told that the time required to execute, and while defining the machine cycle also I have mentioned the word the time required to access the memory, right? And initially while we are discussing about the clock, I have told that clock is nothing but of the operating frequency of the microprocessor. Based upon the clock only the microprocessor runs. So the machine cycle and instruction cycle take multiple clock periods. The clock periods are nothing but of, by means of counting the clock periods, the time required for a instruction or machine cycle is being calculated. So the machine cycle and instruction cycle take multiple clock periods. A portion of an operation carried out in one system clock period is called as T state. In simple, we can say that each clock cycle is called a T state, and number of T states required to perform any operation is called a machine cycle, and number of machine cycles required to fetch and execute an instruction is called an instruction cycle. To execute a program, the 8085 microprocessor performs various operations such as opcode fetch, operand fetch, memory read, memory write, IO write, interrupt acknowledge, ideal machine. The microprocessor external communication functions can be divided into three categories: memory read write operation, IO read write operation, and interrupt request acknowledge operation. Table gives the various possible states of the processor based upon the control signal IO/M bar and S1 and S0. For opcode fetch, memory read and memory write, these three are of memory related operation because opcode is in the memory. In order to fetch the opcode is being given in the memory by means of user. So the opcode should be fetched from the memory. If the microprocessor wants to read a data, again the data is in the memory, so it is a memory related operation. If the microprocessor wants to write something in the memory, it is again a memory related operation. So for the memory related operation, the pin in 8085 microprocessor IO/M bar will be having an active low signal called 0, right? Since IO/M bar is being there, 0 states the microprocessor is doing memory related operation. If the microprocessor is doing any IO related operation, IO write, IO read, or interrupt acknowledge is nothing but the interrupt is being coming from the external device. So it is an input to the microprocessor. Or else if the microprocessor want to send something to the external device, again it is an output. So it is of a IO related operation. So the interrupt acknowledge cycle is a input related thing. So while the microprocessor is performing any IO related operation, the IO/M bar pin will be in active high. When it is performing many memory related operation, then the IO/M bar pin will be having a low state or 0. And the S1 and S0 signals for opcode fetches of 1 1, and for memory write and memory read it will be of 0 1 and 1 0. For IO write, for write operation you simply remember that for write operation the S1 will be 0 and S0 will be of 1, and for read operation it will be of 1 0, right? First we discuss about the opcode fetch machine cycle, right? So the first duty of microprocessor is to fetch the opcode. Here I have shown a diagram of 8085 architecture with some blocks and a memory unit, right? User will be writing the program in the memory, and the duty of microprocessor is to fetch this opcode which is being in the memory. The first duty of the microprocessor is to fetch the opcode. In any instruction, the first the microprocessor fetch the opcode, then it will do the rest of the operations. Here in this example, in 2005 address location, a opcode is being written, and that particular opcode should be read by means of the microprocessor. So this we all know that the program counter's duty is to locate the next instruction to be executed. So the next the 2005 address location is being pointed out by means of the program counter, and that particular address will be obtained through the address bus first, right? Then after getting this address, what the microprocessor have to do, it have to take the data. After taking it is not data, it have to take the opcode. So after taking this opcode will be sent to the microprocessor through the data bus, right? Then after getting this opcode, it will be given to the instruction decoder. The instruction decoder will decode the instruction, right? This is what the flow for any of the instruction. So once the program counter points the next instruction to be fetched by means of the microprocessor, what the microprocessor will do is the control unit in the microprocessor will generate the ALE signal. We know that the address bus in 8085 is of 16 bits, and we also know that the 8085 microprocessor has dedicated higher order address bus A8 to A15 and multiplexed address bar data bus of AD0 to AD7. In order to demultiplex this address and data lines, the ALE signal should be enabled. As this ALE signal goes high, what happens? It is going to demultiplex the address bar data line. So the multiplexed address bar data line will act only as address line once the ALE signal goes high, right? And the next control signal which must be initiated is read, right? By means of enabling this ALE signal, the microprocessor is going to get the lower order address 05 and the higher order address 20 will be obtained through this dedicated higher order address lines. So 2050 is now obtained by means of the address bus. Once this address is being obtained, next duty is to read the opcode. So the control logic unit will release the read bar signal, right? So once this control unit release the read bar signal, the opcode which is in the specified memory location will be read by means of the microprocessor, and it is being carried through the data bus to the microprocessor instruction decoder unit. Okay, so this particular operations are being depicted pictorially in this timing diagram. I will tell you and explain you in detail now. So I will tell you what happens during the first clock cycle. So initially the program counter is locating a memory location and that particular address to be fetched, isn't it or not? So during the first clock cycle, what have to be initiated, what are all the signals have to be initiated, and what operation is being performed here as being depicted, right? So I have told that once this address is being obtained, the address is to be first noted by means of the microprocessor. This particular address to be taken first. So the address will be coming through the address bus. The lower order address to be first noted by means of the microprocessor. So the ALE signal goes high during the first half of the clock cycle, right? The ALE signal will go high during the first half of the clock cycle. That is here it is during the 0 state. What happens? The ALE signal goes high, right? So once the ALE signal goes high, what it will do? We know that once the ALE signal goes high, it is going to demultiplex this lower order address. That is, multiplexed address bar data line is being demultiplexed and only it is going to act as an address line. So as the ALE signal goes high, it latches the address. So the multiplexed address bar data line will act as an address line. So during the first half of the cycle, the ALE signal goes high. As it goes high, the multiplexed address bar data line will act as an address line and it is going to take the lower order address. In this example, it is of 2005. So the lower order address is of 05. That particular lower order address is being obtained. And during the next half of the first clock cycle, what happens? Once the lower order address is being obtained, the ALE signal goes low, right? Then duty of the 8085 microprocessor is to take the higher order address which will be coming from the dedicated address bus, higher order address bus A8 to A15. So during the next half of the first clock cycle, it will be obtaining the higher order address bus. So during the first half cycle of the clock cycle, the ALE signal goes high and the lower order address is being obtained through the lower order address bus. As soon as the ALE signal goes high, the multiplexed address bar data line is demultiplexed and it is going to act only as an address bus, and the lower order address is being fetched. And during the second half of the first clock cycle, the higher order address bus is obtained. Once the lower order and higher order address are being obtained, what the microprocessor have to do? It have to read the opcode which is being written in the memory. I have told that first the ALE signal is being generated and the lower order and higher order address are being taken through the address bus. So that is what happening in the clock 1 cycle of the machine. During the second clock cycle, what happens is that, so now the address is being fetched. The address is being read by means of the microprocessor. The address will be coming through the address bus of the microprocessor, right? So the address is being obtained. Now it has to read this particular opcode which is in the memory. Now this read signal is being enabled by means of the control logic signal. What it has to read? It have to read the opcode which is in the memory, right? So the read signal which is high during the first clock cycle goes low during the second half cycle. Indicate RD bar, since it is of RD bar, when it is in high state, this the microprocessor won't read anything, right? Once it goes low, the microprocessor will read something. So here the address is being fetched during the first half of the clock cycle, clock cycle, and in the second clock cycle it have to read this opcode which is in this particular memory location, right? In order to read this particular opcode, the read bar signal, since it is an active low signal, it will go slow during the second half cycle, second clock cycle, right? During the second clock cycle it is reading the opcode, and this will continue till the third cycle too. Once this opcode is being read, what it has to do? It has to decode it. That will happen in the remaining cycle. I will be telling now. So until the third cycle, the opcode is being read. So during the first clock cycle, the lower order and higher order address are being fetched. So the lower order address is being fetched by means of ALE signal. The ALE signal goes high for the first half of the clock cycle, and once the ALE signal goes low, the lower order address is being fetched by means of the address lines. That is, the address bar data line is demultiplexed and it is going to act only as the address line, and the lower order address is being fetched. Then the higher order address is coming directly from the higher order address bus A8 to A15. As soon as the address is being fetched by means of the microprocessor, it has to read the opcode which is being in the particular address location, right? So here the opcode is 4F. This 4F should be read by means of the microprocessor. So during the second half cycle, during the second clock cycle, the microprocessor will generate the read signal. Since it is of an active low signal, during the first clock cycle it is active high, and during the second half cycle it becomes active low. As soon as it becomes active low, it is going to read the opcode which is being in the memory location, and this read cycle will continue till the T3. Next, in the T4 cycle, what we will do is, in the T4 cycle, after fetching the opcode, what the microprocessor have to do? The microprocessor have to decode it. So during the T4 cycle, the fetched opcode is being decoded and
it is being converted to the machine language, that is it is being converted to binary form. So during the T4 cycle, the fetched opcode is converted to machine language or binary form. The hexacode is being converted to binary form, right? So at the end of the T3 cycle, the read signal is disabled and it goes to active high. So during the T4 clock cycle, it is of active high, because in the T4 cycle I have told that the microprocessor is only going to do the instruction decoding. The fetched opcode is being decoded. No read or no write operation is being performed, right? So it is going to decode that particular instruction, right? So this IO/M bar is nothing but of the status signal or status of the microprocessor, which while performing this opcode cycle. So here the opcode fetches a memory related operation, so IO/M bar is of 0 and S0 and S1 lines are of 1 1, right? That is being indicated by means of this IO/M bar. I will repeat this complete timing diagram once again, because once you understand this, you can easily understand rest of the timing diagrams. So the first duty is to fetch the opcode, right? In order to get the opcode, the address where the opcode is being written should be first obtained by means of the microprocessor. The address is being obtained by means of the address bus. We know that here in 8085 the address is, the lower order address is multiplexed with the data lines and the higher order address is of dedicated. So in order to demultiplex it, what the microprocessor will do, during the first clock cycle, the ALE signal, during the first half of the clock cycle, the ALE signal goes high. As soon as the ALE signal goes high during the first half of the clock cycle, the multiplexed address bar data line are being demultiplexed and it is going to act only as the address line. So the lower order address, here in this example it is of 05, is being obtained, or it will be coming through the lower order address bus, and the higher order address bus is being obtained through the higher order address bus. So here it is of 20. So once the address is being obtained, the microprocessor duty is to read the opcode which is being in the address location. So in order to read this particular address, the microprocessor control logic unit have to release the read bar signal. So during the clock cycle 1, the read bar signal is of high. Since it's active low signal, it is high during the first clock cycle. In the first clock cycle, just it is going to get the address. So no read or write operation is being performed. So the RD bar signal is of active high. So during the second clock cycle, it has to read, now the address is being obtained, it has to read the opcode which is being in the address location. So the RD bar signal goes low. Once it goes low, the opcode which is in the address location is being read by means of the microprocessor, and this read operation continues till the next clock cycle, that is T3 cycle also performs the opcode fetch, or the opcode is being read during the T2 and T3 clock cycle of the microprocessor. After reading this opcode, the RD bar signal goes high during the T4 clock cycle, and in the T4 clock cycle, what the microprocessor will do is, address is obtained, opcode is being read. Next, the duty of microprocessor is to decode this opcode. So decoding operation is being performed during the T4 cycle, right? And the status of the signals during the opcode fetch cycle is being indicated here, right? So it is a memory related operation. So IO/M bar is of 0, S0 is equal to 1, S1 is equal to 1 for opcode cycle. We have seen it in the table, right? So that is being depicted over here. Hope you are clear with this opcode fetch instruction. Next, we see about the memory read machine cycle. This memory read machine cycle has 3 T states, right? So as I have told previously, in order to read something from the memory, what it has to do, the microprocessor must have to first know the address. In order to know the address, as I have told, during the first clock cycle, the ALE signal goes high during the first half of the first clock cycle. As soon as the ALE signal goes high, the lower order address is being fetched. After fetching the lower order address bus, the higher order address will be coming from the dedicated higher order address bus. So the address is being completely obtained through the higher and lower order address bus now. So that happens on the first clock cycle. The next clock cycle, what it has to do? The address is being known now. It has to read simply the data, what is being in the memory. So during the T2 cycle, the read bar signal will go slow and it continues till the T3 cycle and the data is being read. Right? So the status signal for memory read is being shown here. In order to fetch the address, lower order and higher order address, what the microprocessor is going to do, it is going to generate the ALE signal first during the first clock cycle. As soon as the ALE signal goes high for the first half of the first clock cycle, the multiplex address bar data line is being demultiplexed and the lower order address is being obtained and the higher order address is being obtained through the dedicated address line. Once the address is being obtained, it has to read the data. So the data read is being done during the T2 and T3 cycle. So during the T1 cycle, the read bar signal is of high and it goes low during the T2 and T3 cycle and the data is being read. Clear with this? Next, as of IO read, the IO read operation is much similar to that of IO memory read. Only the status signals change over here. Instead of reading the memory address, IO addresses are being read. Right? All other operation remains same. Only the status signal change. Right? Since it is of IO operation, there in memory read we have stated it as 0. Since it is of IO related operation, IO slash M bar is equal to 1 and the status signal S1 and S0 will be of 1 and 0 as we have seen in the memory read operation. Next, memory write. So for memory write operation, again it is a memory related operation. It has to read the address first. In order to read the address, in order to read the lower order address, what the microprocessor will do in the first clock cycle? The ALE signal goes high for the first half of the first clock cycle. As soon as the ALE signal goes high, the lower order address will be coming through the lower order address bus. The ALE signal will demultiplex this address bar data line and the multiplex address bar data line will act as an address line only and it is going to take the lower order address. As soon as the lower order address and higher order address are being obtained by means of the dedicated higher order address line and the lower order demultiplexed address line, the data should be written. Here the microprocessor is going to write something in the memory. So in order to write, instead the WR signal goes low. There, in order to read, the signal have to go low, the read bar signal. Here, since it is of a write operation, WR signal will be activated, and since it is a active low signal, it remains high during the T1 and T1 clock cycle, and during the T2 clock cycle it goes low. As soon as it goes low, the microprocessor will write some data in the address what it has fetched or what it has obtained during the first clock cycle. The status signal for it is shown here. Right? I will summarize once again. In the T1 clock cycle, the higher order address bus A8 to A15 and the lower order address and data multiplex AD0 to AD7 bus is going to take the address. The ALE signal goes high so that the memory latches AD0, AD7, so that So the complete 16 address are being available and the address is being taken. The MUP identifies the memory read machine cycle from the status signal IO slash M bar 0, S1 equal to 0 and S0 is equal to 1. This condition indicates memory write machine cycle. During the T2 state, it selects the memory location in which the data should be returned and the ALE signal goes low during the T2 and T3 cycle. Since it has to write the data in the memory, the WR bar signal goes low and the microprocessor starts writing the data. The IO write machine cycle is similar to that of the memory write. Only the status signal change over here. Instead of getting the memory address, the port address are being obtained here. Now we will see some examples. Right here, the example taken here is of move immediate B, 43H. Right. So you assume that move immediate B, 43H is written the address location 2000. We know that this move immediate B, 43H is a 2-byte instruction because move immediate B has an opcode and that particular opcode will be in the address location 2000 and the data, immediate data which should be moved to the B register will be in the next address location, consecutive address location 2001. So it is a 2-byte instruction. So first duty of microprocessor is to fetch this opcode, right? So it has to fetch the opcode first. After fetching the opcode, what the microprocessor have to do? It have to read this particular data, isn't it or not? So after reading it, only it can move it to the B register, right? So first duty of microprocessor is opcode fetch. After reading the opcode, after doing the opcode fetch, it has to read this particular data. So this move immediate B, 43H has opcode fetch followed by means of a memory read. So opcode fetch has 4 clock cycles and memory read has 3 clock cycles. We have seen it separately in the previous discussion, right? So if we want to draw the timing diagram for move immediate B, any 8-bit data, it consists of opcode fetch machine cycle followed by means of a memory read, right? So first it has to fetch the opcode. In order to fetch the opcode, it has to first know the address. So the address to be first known. So in order to know the address, what happens during the first clock cycle? The ALE goes high during the first half of the first clock cycle. As soon as the ALE signal goes high, the multiplexed address bar data lines are being demultiplexed and the lower order address and higher order address are being fetched. So 00 will come from the lower order address line and 20 will be coming from the higher order address line. Once the address is being obtained, what is the duty of microprocessor? It has to fetch this opcode. It has to read this opcode. So in order to read this opcode, the RD bar signal must go low. So during the first clock cycle, the RD bar will be of high, and during the second and third clock cycle, the RD bar signal goes low and the opcode 06 is being now read by means of the microprocessor, and during the T4 cycle, the microprocessor will decode this particular opcode and will come to know that the user has instructed to load a immediate 8-bit data into the B register, right? So that is being known during this T4 cycle. Once it is being known, the next duty of the microprocessor is to read the 8-bit data, because by means of decoding, the microprocessor comes to know that immediate data should be loaded in the B register and the user has specified immediate data. So by means of fetching the opcode, the processor comes to know that immediately it has to move a 8-bit data. As soon as the decode operation is being done, the next duty of the microprocessor is to read this immediate data which is being given by means of the user. The data, immediate data is in the consecutive memory location, because only a 8-bit of code or data can be stored in a 16-bit address. So 06 is a 8-bit opcode which is being in the location 2000, that is being fetched in the opcode fetch cycle. Next it has to take the data 43H, right? So what again it has to do? It has to get this particular address location. That particular address locations are being obtained during the first clock cycle of memory read. So the ALE signal once again goes high. As soon as the ALE signal goes high, the address bar data bus is demultiplexed and the lower order address 01 is being fetched, and the higher order address will be coming through the dedicated address bar address line. So 2001 address is now obtained through the address bus. As soon as this 2001 address is being obtained, next the duty of the microprocessor is just simply it has to read, right? Already it has decoded and it came to know that the user has instructed to read the immediate data which is being given by means of the user to, it should be read and it should be moved to be registered. So now it will be reading the data which is being in the address location 2001. So in order to read the data, the RD bar signal should be low, right? It will remain high once the opcode is being fetched, and once again it goes low in order to read this data. So after reading the data, the process completes and the complete machine cycle comes to an end. This is how we have to draw the timing diagram for all the instructions, right? I will show in some few more examples to draw the timing diagram, right? Next example what we chose here is of store accumulator, right? Store accumulator followed by means of a 16-bit address. Here the address what we have chosen here as of 5268, right? This is nothing but of a 16-bit address, right? What this instruction will do? It will store permanently the accumulator data in the specified 16-bit address, right? Accumulator is holding a 8-bit data temporarily. That temporary data is being permanently stored in this 16-bit address, right? We all know that this store accumulator 5226 is a 3-byte instruction, because store accumulator has a opcode and that opcode will be in address location. After reading this opcode, the microprocessor have to read this address 5226, right? So that will be in the next consecutive address location. After reading this address, what the microprocessor have to do? It has to write the data which is being in the accumulator in this memory location. That is what this instruction does. That is, it has to store the accumulator content in the specified address location. In order to store the accumulator content in the specified 16-bit address location, first the microprocessor have to fetch the opcode for the store accumulator. By means of fetching this opcode, the microprocessor will decode this particular opcode and it will come to know that the user has specified to store something in a address location, right? After decoding it, what it has to do? It has to read the address location where the accumulator data should be stored. So next it has to read this particular address. After reading the address, what it have to do? It have to write the content what is being in the accumulator to this address location, right? It has to store or it has to write the accumulator content in the specified address location, user specified address location permanently. Accumulator is holding temporarily a data. That temporarily holded data should be moved to a specified user specified address location. So first the opcode is being fetched. By means of decoding the operation, the microprocessor will come to know that the user has instructed the microprocessor to store permanently the accumulator content in an address location. So after decoding, it has to read the address location. Then after reading the address location, it has to store, or it has to write that particular accumulator content in the user specified address location. So the store accumulator consists of opcode fetch followed by means of memory read, right? So one memory read is to read this 6A address, in another memory read is to read the 52 address. Next, after reading this address, it has to write the data which is being in the accumulator, right? So the store accumulator consists of opcode fetch followed by means of two memory read and memory write. So opcode fetch cycle is to fetch the opcode for store accumulator. The opcode for store accumulator is 32. The 32 is being fetched during the opcode fetch machine cycle. After this opcode is being fetched, it is being decoded during the opcode fetch machine cycle. And in the next cycle is memory read. So 6A is nothing but of the lower order address what we have specified, that 6A will be in the next address location, right? That should be read by means of the microprocessor. So a memory read cycle is being followed. 6A, the lower order address, is being read by means of the microprocessor here. After reading this, then it has to read the higher order address what the user has specified, that is 52 in this example, that is in 4201. So that particular higher order address is being read next. After reading the lower order address 6A and 52, now the microprocessor has obtained the memory location where it has to store the accumulator content permanently, right? So it has to write the content what is being in the accumulator in the address location 526A now. So now a memory write machine cycle is being followed by means of memory read. Here since the address location is being obtained, 526A is being obtained, in this 526A address location a data is being written. You assume that data as C7, or else it can be of any data, right? That particular data will be written in the specified user specified memory location. So the opcode is being fetched, then the lower order higher order memories are being read. After reading the higher order and lower order address, the data is being written in the specified address location, right? So the store accumulator consists of opcode fetch cycle followed by means of memory read, two memory read and a memory write, and it consists of totally 13 T states. Hope you have understood what is the timing diagram, what is the need for it, and how to draw the timing diagram for the 8085 instruction. Now it's time for assignment. You try to draw the timing diagram for the following instructions what I have specified here: add M, INX followed by means of a 16-bit address, IN followed by means of a port address, and LXI followed by means of a 16-bit address. You try to draw the timing diagram for these instructions and post it in the Moodle class. Okay.